All right, I think that we will get started. We're a minute after the top of the hour. So once again, good morning or good day, everyone, depending upon your time zone. My name is David Failing. I'm with Lucas Diesel Systems. And on behalf of Lucas Diesel Systems, I'd like to thank everyone for joining us today on the last session or last training session that Lucas Diesel sponsors for the year. So I'd like to take this opportunity once again to thank everyone. Appreciate you taking the time out of the day to join us. A few housekeeping items before we get started. One of them is for those of you who are participating and are participating for the entire length of the webinar here, you will receive a certificate within a couple of days from Lucas, and that will be through your email that you signed up for to participate in this class. The other thing is, in order to reduce any distractions, we have muted everyone. So if you need to communicate or ask any questions and so forth, please put them in the chat, and then we will be able to address the questions maybe as we go along, and or if not, we will have a time slot at the end of the session in order to be able to answer any questions. Replays of this webinar will be on the Lucas Diesel Systems YouTube channel, as well as on Tony's website. So if you need to look at another portion of the webinar, or you want to share this with anyone in your company, you're welcome to do so, and say it's available on the Lucas YouTube channel. Let me see. Before we get started, I'd like you to please consider Lucas in your diesel fuel injection system needs. As your need arises, we have a complete set of an enormous amount of parts, and so please consider Lucas Diesel Systems on your needs in the future for any of your parts. Our presenter today is Tony Salas. Tony is a veteran technician as well as an instructor, and he resides in Las Vegas, and he has a shop there as well as a training company, and it's called Powertrain Training. So without further ado, I'd like to hand it over to Tony, who will be speaking on cam and crank position sensors and giving us an overview today. Thank you, Tony.
Thank you, Mr. David. Good morning, good afternoon, everybody. And those of you watching the recording, well, hello, whatever time you're watching. Well, it's December already. God, what day are we in? 17th.
17.
It's a day, time goes by fast. It's been nice. Lucas sponsoring pretty much almost every month these webinars for you guys. We like to thank you, and everybody that I work with Lucas Diesel and sponsoring this, I'd like to thank you. And again, we like to see you guys always learning something new. So when we can get some cheap education, that's a good thing, ain't it? So definitely want to support our sponsors, and in this case, Lucas Diesel being one of them. So the topic of today is crankshaft and camshaft position sensors. Those of you that have seen my training over and over, I'm very an instructor that also believes in repetition, so it actually sinks in your head. And in this case, kind of when you come up with these presentations, when I work on these presentations, I said, okay, what am I going to cover? What am I going to teach? I got so much time, and the question begs, what is a good hot topic? So the crankshaft camshaft position sensors obviously have been around for years, and they've been used extensively ever since the LB7 for starters, when we saw that being introduced in 2001, and we saw cam sensors being used on other applications too as well. If we go back to the 7.3s, right, where we were just using a good, I guess what I'm trying to say is having a good education on how they work. So again, how does this stuff work? So therefore, yes, crankshaft and camshaft position sensors are very important in the function. They're part of the whole family of sensors that are serious inputs for the proper function of the engine, but also for fuel economy, drivability, and power. Definitely got to have that power. So why presentation on the crankshaft and camshaft? Because of the importance of their input. Their input is very critical as well. So obviously we need to have a sync, because we live in an era nowadays where we just turn the key and the engine just runs. So therefore, there is no timing to be done. There's no pump to put on time to get that engine to actually work right. Heck, we're not even bleeding air hardly ever anymore. So therefore, air is, for initial startups after repair or assembly is not required. So again, thanks to the inputs from the crank and cam sensors working together to go ahead and sync and start firing the firing order. And so therefore we inject those injectors. So unlike gasoline, where gasoline has ignition and injector timing, diesel pretty much is all about the injection on time. So we want that injection on time to be correct. Now, don't get me wrong, there are other sensors that are important because we have a desired and actual rail pressure, and that is made by a series of inputs such as your barrel, your map, and other temperature sensors as well. But in this case, we need that input. How do we know that that engine is turning? I have seen some people talk to me about using other people to tell them, in other words, tech hotlines, or, I see postings from other technicians and instructors talking about that crank and cam input. But when I hear things such as, and this is the second time I hear it, where I see that, well, if you got a crank no start and you're not getting lip pump operation, you need to focus on that before you focus on the crank cam problem. In other words, I'm going ahead and scanning. I'm doing a crank no start, crank no start. And at that point, I see that I'm losing the RPM signal. So where do we derive that RPM signal? Primarily from the crank and cam sensors. So a classic thing that most of you probably do. If you don't, well, guess what? You should do it. In the event you question the crank and cam input, quickly look for an RPM signal, even from the old days of 7.3 Powerstroke. So therefore, yeah, we need that input, because if upon seeing no revolutions or RPM, the lip pump will only have a prime, which is usually a 30-second runtime, and then it'll just shut off. So how many times have we seen crank issues or no start issues, where in this case, we just don't see lip pump operation? And when I see the changes in lip pump operation, like the L5P Duramax, where we're now using a 3-phase pump with a fuel pump control module, that changes the game a little bit more too, because there's a signal that needs to be sent out to that module to enable the lip pump. Regardless, though, it's all about, also, like I said, in the bullet right there is the fuel injector timing. In other words, when are we going to fire off that injector? But on the diagnostic portion of it and the emissions portion, we have misfire diagnosis, right? So in this case, we need to analyze how we're going to, how does the computer come up with a conclusion that, yes, I do have a misfire? As I'm teaching L5P Duramax this past week, it was talking about using the misfire history and current misfires on your scan data to establish, do you have a misfire, right? But then you got fuel trims. How do we derive fuel trims? There's no oxygen sensor per se. Yes, we can use the NOx sensors, but the primary input for misfire and fuel trimming and information on balancing rates and input is actually your crank and cam input. So therefore, that timing and quantity is very important. So as I've stated before on my L5P class, I was talking about, how do we derive that angular velocity, because there's something called angular velocity to actually diagnose a misfire on these engines. So the number one component is, again, the crank sensor. As we can see, the crank on typical V8 engine will actually turn twice for one of the camshaft. But in this case, we're looking at the signals that are being generated, whether being a Hall effect style trigger or a AC generator like we use on older applications. So therefore, the crank sensors and the cam sensors can vary, but in this case, that crank sensor input is pretty critical. Now, I will mention it again, but I'll just briefly say it right now, but the integrity of that crankshaft or camshaft is very important. Exactly that, in other words, meaning that is the reluctor wheel running true? Is it loose? Is it wiggle? As it shifted? So in this case, that's something we can establish with the crank sensor, which in turn can fool the computer and actually cause various different crazy issues. So the point is, the crank sensor is extensively used when it comes to the misfire diagnosis. Now, one thing I've been teaching lately is the use of mode 6 in your scan tools. And in this case, that's your generic mode, so you can establish, do you have a misfire that maybe you see a code set, but you can't see it live. So mode 6 might be your best friend, because the computer does keep a file on each cylinder. Now, again, The crank sensor provides the angular velocity signal. So as you can see from this circle that I drew this with an X and Y axis, you're going to notice that I'm just showing the time and the time frame of when a cylinder fires, it actually momentarily speeds up the crankshaft, especially at idle periods. So in this case, when that occurs, the computer will see from the crank sensor the actual change in speed of the signal that was being generated. And we'll look at some signals here in a little bit. But again, that is what the computer is doing. So if you look at the automotive world, they've been actually using lab scopes to look at these waveforms. And in this case, that helps a lot in your diagnosis. But for now, all we're just trying to say is the importance of that crank sensor is dependent on, again, that crankshaft spinning along with the camshaft also spinning as well. So in turn, the computer can see which cylinder is actually speeding up or slowing down the crankshaft, meaning that it's not contributing the same amount of power. So in this case, that's what the computer uses as a main input. So your diagnosis, issues can vary, which are related to cam. And I've seen some crazy stuff that I never thought I would see. You think it's cut and dry, but it's not always. So on one hand, we got the signal integrity. On the other hand, we got the reference voltage. We got the signal return, right? We also have wiring and connector issues too as well. But then physically, like I mentioned earlier, the integrity of that crankshaft. For example, when we were dealing with Powerstroke 6 liters, we actually found a lot of thrust play on the crankshaft. And what would happen was that sometimes you get an intermittent start. Sometimes it would sync, sometimes it won't sync. And what's literally happened is if you take the crank sensor out, you stick a borescope in there and have somebody crank the engine, you'll literally see that reluctor wheel moving side to side, which is indicative of excessive thrust play on the crankshaft. So those things I never thought I'd see, but this was mostly on those engines that had manual transmissions. So in this case, what I'm trying to say is, what's the overall condition of the engine can actually fool. But then we got clearance issues. And what I mean by clearance issues is that there are some guys that literally have had to shave the base of that crank or cam sensor, mostly crank, and literally actually have it sink in more into its bore because this aftermarket was not actually given a proper signal. So in this case, what was the fix? Literally shaving the base and actually with a Dremel or something like that and actually put it back in and actually would trigger a signal because we can see it on the scope. So overall, what I'm trying to say is expect the unexpected, especially when you're dealing with aftermarket. But the truth is, we have seen this, I have seen it, that aftermarket and OE replacement sensors, as much as we try to buy a good quality part, OE sensors have also failed too, and have been an issue where there are varied engine running issues. I remember actually replacing a cam sensor on a 7.3, and yes, it was an aftermarket. I won't name names, but the truck ran great for 3 months. The customer brought it back after 3 months, and what happened? It would actually run rough between about 1,200 RPM to about 2,200 RPM. And right after 22, it just ran smooth. It had this window where it was just running rough, and turns out we had a defective cam sensor. So, and another thing we got to keep in mind is, when you're doing diagnostics, I just discussed this with a shop last week, and sometimes time is money. Okay, time is money. And one of the things that a lot of us have in our toolboxes, in our drawers, is you might have a spare cam sensor for a 7.3, because by the time you hook up and try to get a signal, which is faster to determine the issue, either put in a cam sensor or actually try to scope it. But is it easy to get to the connector? No. Is it easy to get to the ECM? Nope. So in this case, sometimes we have to think with our brains, because again, time is money. I take no pleasure in putting a sample part for testing purposes, but sometimes due to the time constraints and everything involved, just to do a proper diagnosis is not easy. So keep that in mind. But again, engine and crank integrity along with the reluctor wheel can be issues. A Duramax, for example, I remember the LB7 LLY days where that reluctor wheel has bolts that actually bolt it onto the actual crank. And in this case, those were known to come loose after time, and that would actually cause erratic behavior to eventually not starting. And then we got wiring and connectors. I attribute a lot of the wiring and connector issues to technician abuse. And what I mean by technician abuse is that they're doing a repair. Let's say they're doing some other major engine repair or water pump front cover, I don't know, whatever it might be. And the problem is that they just tuck and pull on harness. We live in an era now where we really have to be really nice to wiring connectors, and again, moving those harnesses nice and neat out of the way and not stressing them. So as we look at these big three, when we talk about the cam and crank, Obviously, there's going to be a series of codes that they set and that can actually help you understand. But like I've been finding out as I talk to techs, as I go out to the different shops, is that a lot of you are just not reading codes. I mean, bottom line, you're not reading codes. You're just trying to find the quick fix and you're not spending the time. So therefore, I'm trying to sell you on the fact that the service information is critical. You got to read those diagnostic trouble codes. And if you're new to this or just not very well, you got to understand, okay, A, I have a code. B, I have a drivability problem or a no start problem or hard start. And in this case, you're going to have to view what each manufacturer does. Now, I'm a big user of Identifix. Those of you that use your pro demands and all data, I'm not docking you. But in this case, they're using the same information they copy and paste over from the manufacturer. So in this case, there is a descriptor that tells us about the code. And in this case, it's Crankshaft Position System Variation Not Learned. Okay, this is a very common GM thing on General Motors truck. And it clearly says in the description that the crankshaft position sensor variation or reluctor ring learn is used to calculate the reference period errors caused by slight tolerance variations in the crankshaft and crankshaft position sensor. The calculator allows the ECM to detect misfire events over a wider range of engine speed and load, and the compensation values are stored in ECM memory after a learned procedure has been performed. This most likely occurred after reflash or after a major repair or replacement of the ECM. So in this case, we're supposed to do that. And also you're supposed to do it upon replacement of crank and cam sensors. So this is something you can execute with the scan tool that actually makes life a lot easier. So with that said, again, you're trying to understand, okay, I got a crank and cam issue. What is it? How is it that the engine runs? But I got this code. Well, again, reading is actually very good. And as I continue pulling out General Motors service information on Duramax, you got a PL335, you got a PL336, and in this case, you're going to notice the titles. It's important to look at the titles. And the titles are Crankshaft Position Sensor Circuit, while 336 is the actual sensor performance. Now, as you look at the diagnostic troubleshooting charts off of GM from the factory, you're going to notice that a code is referencing what is going on with the circuitry going to the sensor itself. We got 5-volt reference, we got signal, we got low reference. So the question begs, okay, what is each code doing? Now, the 5-volt reference and the short to ground can have a variety of codes because that reference voltage is shared with other sensors that are affected too as well. So when you got a 5-volt reference that is pretty much, shorted to ground or actually shorted to voltage, that truck will definitely not start, but actually have mega codes because it'll affect many sensors. And we'll see that in the wiring diagrams. However, though, when you got an open or high resistance, it's a PO335, again, a circuit issue. When you look at a short to voltage, you're going to see PO558, PO651, 11.8C, right? And then you got signal performance. In this case, that's the PO336. But again, the short to ground high resistance faults, again, will be related to the 335. Because I hate it when a guy wants to scope a signal already on a 335. I go, no, dude, you got a sensor, you got a circuit problem. You got to check the integrity of those 3 wires that usually go to most conventional crank and cam sensors. And in this case, the reference voltage, the signal return, and the signal itself. That's actually, your signal for the position itself. So again, what I'm trying to sell you on is the reading. Now, if you're new to this and you don't know all the 3 wires or 3 typical connectors that we see, 3 terminals that we see on a sensor, whether being a cam or crank, is the 5-volt reference, which is the regulated voltage supplied by the ECM. And then we got a signal. That is the actual manipulated signal that comes from the sensor itself once it starts to work. And then you got low reference, which is, again, the ground that goes through the control module. So definitely ground is very important. That's why I'm a big advocate that when we see issues with ECMs and stuff, and the truck has been through some major, maybe somebody tapped into it, but whether it being a cab off repair, whether it being a big engine repair, it kind of questions the fact that are all the grounds in proper order and tightened, and this will affect your low reference. So if you got a bad ground going to the the ECM PCM, and you're also providing that same ground through the path through the ECM, kind of questions how that low reference is going to be. That's why I've always been an advocate of doing voltage drop testing. Again, we want to put that meter across that low reference and that 5 volt reference. And in this case, you're just going from 5 volt reference to ground to ensure that you do indeed have a good reference circuit, right? So, you're going to see some changes with General Motors too, because in this case, they seem to be shifting to an alphanumeric code for components, such as the European market, like the Germans. And in this case, we see crankshaft position sensor there, right? And in this case, you see B26. And that B26 is actually the crankshaft position sensor. The engine control module is now known as K20. So in this case, I've learned to memorize that one K20 because it kind of reminds me of 4x4 Blazer because it was a K series and 20 series, but that's the way my brain works to memorize this. But again, using the description and operation and using the diagnostic trouble code information, this is where I got it from, the codes, and understanding what you're dealing with. So if I ask you, hey, how does a crankshaft position sensor work? So I thought I used this slide. And it says there, it contains a Hall effect sensor and additional electronics that processes the signal because it's DC in nature. So as we will learn here in a second here, the types of signals we're going to get, depending on the manufacturer and your model. Crankshaft and camshaft position sensors can be Hall effect or they can be variable reluctance. And Hall effect means that it generates a DC signal, but in order to generate DC signal, it's got to have a reference voltage applied to it, which is usually 5 volts. Okay. Then you got the variable reluctance sensors, which are AC in nature. They generate an AC signal. Now, don't get me wrong. ECMs, PCMs do not like DC signals. They like DC signals. So if a sensor is generating an AC signal, that must mean that there's got to be a buffer that we used to use in the early years, but now that's all integrated into the ECM, PCMs, where it actually translates that AC signal into a DC signal. That's what you're going to see. Regardless, though, if we look at the Hall effect as described here on this box here, it detects the change of strength of the magnetic field caused by the reluctor ring. So in this case, that every sensor will have a magnet built into it. That's where we actually get the ability to actually strengthen and weaken that magnetic field. So with the strength changes, the sensor changes the amount of current it consumes. This results in a square wave signal of the current while the voltage stays constant. Now, the control module detects the frequency in which the current changes, which is proportional to rotational speed. So what I've done here, just to give you an idea, might as well just do this. I'm going to change here for a second, and let me know you can all see my my scope here. Can you all see my scope? Let me know if you can see it. And in this case, what I'm just simply going to do is I'm going to go ahead and change my settings here. You should see a scope in front of you. Hopefully you all can. And in this case, what we are seeing there is a nice scope signal. Thank you for letting me know. Yep, good. Thank you, Carl. And in this case, what we're looking at is indeed a Hall effect signal that's being generated. It's all live right now. So in this case, two things I'm trying to showcase here is number one is I'm actually showing the actual signal of a crank signal. And I haven't yet put the cam sensor signal yet, but again, we can see the crank sensor signal. You will notice, if hopefully you can all see it on your screen, this is how zoom I can go. So I'm sorry if it isn't good enough, but it is a 0 to 5 volt signal. We are looking at for the cleanest signal that we can find. And one thing I'm always pushing on when I do scope signal, especially as I've been doing a lot lately, is make sure you have a good ground. So therefore, I am grounded here on my simulator. I am using a live simulator here. And in this case, we're looking at a 0 to 5 volt signal. Now, as I go ahead and pause this, you're going to see the sync signal. And when we talk about a sync signal, we're talking about that gap that you see there. Now, this could be indicative of an issue. Obviously, the reluctor wheels for all different manufacturers is going to be different. So we have to know what a good waveform. That's why a good instructor, Jim Wilson, that I do a lot of work with, one thing that he says about lab scopes is that if you want to learn how to lab scope, work first on a known good truck. So like last week, we were working on a Powerstroke 6.7, and we took a lot of waveforms of the crank and cam sensors. So in the event I do have a drivability issue, it's a good idea to have some saved files that allow me to view a good known sensor. So something to keep in mind. But what I can clearly see here, is the fact that we said it uses a reference voltage of 5 volts. So here we can see the 5-volt signal. If you can see it from the scale 0 to 5 volt right there where my cursor's at. And in this case, we can see it is a rather healthy signal. Now, the actual sync signals, it all depends how the teeth arrangement are set up. Is it missing one tooth? Is it missing two tooth? Well, that's a question. And if the teeth are evenly spaced, because if I look right here where my cursor's at, we got a long gap there compared to the rest of them. So kind of questions, is there an issue there, or is that normal for this application? And that's something we have to see on a known good truck. Definitely want to understand that. Now, when we actually do really in-depth diagnosis, we also like to compare it with the, you guessed it, the cam sensor. So let me go ahead and hook up my cam reading. And therefore, don't make me look like a liar here. If not, I'm gonna have to work on this. But in this case, I'm trying to get a cam reading now, which my scope is not cooperating right now. But I guess we're trying to see it. It's on the bottom here. We're trying to get a signal. But in this case, my settings should be the same. If I look at my settings, I'm on the 10-volt scale at 5 milliseconds. But in this case, I can actually see both signals, which I'm not seeing right now. I guess my simulator's acting up. Let me turn it off. And, oh, it's because I'm playing a recording. I'm not live. That's why. So let me go back. So let me go back to 4-channel scope. And now we have both signals right there. So in this case, the scales are going to be different. If you look at the scale on the far left, you're going to see also it's a 0 to 5. I can change the time base a little bit to actually adjust them. But something we can do is the cam trigger also syncing up with the crank trigger as well, which I can freeze the image and show as well. But for now, all I'm just trying to say is that, are we understanding that it is a 0 to 5 volt signal on most applications? You know, some will vary, but they're almost about the same, and that's something we want to do. So if you're not a scope savvy kind of person, one thing I've been doing at shops is, and they have, many of them have scopes, and in this case, we've been just scoping because in reality, all you really have to understand is how to hook it up, first of all, which is just 2 leads. And the other thing is actually knowing how to change your time setting and your voltage setting. I'm at 10 volts for division. You'll notice right here, I can actually change the time. And that's what I mostly fundamentally teach to the guys. I mean, we can teach triggers and, you know, which way I want to go on the signal. But in this case, how many channels you set up. But in this case, I'm at 10 volt scale and 5 milliseconds time. So I can change that. But all I'm just trying to say is playing around where it actually looks the best, because a common novice question I get about scoping signals such as your crank and cam is, I don't know where to set the settings. Well, you just play around with the time and the voltage where the image looks readable for you, and that's what you're literally trying to do. The more amplified it is, the bigger it is, the more you can scrutinize that signal to see if there's any issues. Now, there are numerous waveform libraries out there where you can actually see interference too, where I can look at this signal right here, and what will happen is that I'm going to see some hash or some serious interference of electromagnetic fields that can exist. The one that I've been saying for years is that I saw a misfire. This was on a car though, but in this case, I had a misfire, and the misfire had nothing to do with the crank and cam sensors. The misfire was actually caused by the electromagnetism generated by the cooling system. One thing, if you look back and you Google it, if you like, is actually doing an electrolysis check on the cooling system, where we actually have voltage being generated in the cooling system, where you literally stick the lead, on your, in other words, the lead off your meter, put it in the coolant and the other one to ground, and you might see some voltage. Any voltage is indicative of that you actually have electrolysis. So, but again, that's another class in itself. But all I'm just trying to say is that, you know, when you look at away from like what I'm looking at right now, it's very, the quality of that signal is dependent on, you know, hey, is it influenced by another circuit, or is there some electromagnetism that's causing this thing to act loopy, you know? So therefore, definitely want to pay attention to that in terms of, you know, what am I really looking at, right? So, all right, we're going to change back to our PowerPoint here. You should have changed the screen there. And in this case, so therefore, as we just saw and we just read, is that this results in a square wave signal of the current while the voltage stays constant. We saw that 0 to 5, right? So the control module detects the frequency in which the current changes, which is proportional to the speed of that crankshaft or that reluctor wheel. So, And then you got your ECM, then you got your reluctor reel. And I could read on this one. Obviously, the simulator I have right now is not the same as interpreted here, but it tells you that there are 58 teeth or invisible magnetic segments on the edge of the crankshaft position reluctor ring mounted on the crankshaft, and each tooth or magnetic segment on the ring is placed at a 60 segment spacing with 2 missing segments for a reference gap, which is usually number 1 reference. So in this case, all we're just trying to tell you is that, again, this information is available for you to read. Obviously, if you go to waveform libraries that are out there, just, IATN and other websites have their waveform libraries where you can see good known signals. But it is my opinion that if you really want to master that crank and cam sensor, is what you want to do is you want to go ahead and, definitely, work on a known good vehicle and do some testing yourself. Again, this will make you a better technician, especially when you want to scrutinize that crank and cam sensor. But yet we have our diagnostic trouble codes going back to where we were. And in this case, the PL335, it's going to tell you the conditions that it actually looks for in order to have that code fail. Now, this is a type A code, which means that it only has to fail once to turn on the mill or the check engine light. And in this case, you're going to see no signal, but it has to be greater than what? 4 seconds. And then again, for conditions 2, has to be greater than 0.3 of a second. These are different conditions, by the way. And then you got condition 3, which is no signal during 2 engine revolutions. So it doesn't take much to set that 335 code, does it? So in this case, it helps, again, you, the technician, knowing that, hey, I'm not getting no signal. But then you got your 336, which is the synchronization. Some of you may have been seeing some YouTube videos or TikToks out there talking about the reluctor wheels shifting on these crankshafts, especially on the 6.7 liter, because they're not actually notched with a pin. So they are shifting, but we've seen that before, even on reluctor wheels on camshafts, on dual overhead camshafts on gasoline applications. So those have been known to shift too as well. In other words, it's no longer time, it's just off a tooth maybe. So with that said, you got to do a little reading, going back to what I said, and understanding what triggers, And condition 3 could be that the crankshaft literally broke in half. How many of us have seen that? Literally broke in half, where one side is spinning, the other side is not spinning at all, depending where the broke is, that is. But in this case, it says, hey, no sync gap was ever detected. So that's pretty funny, but definitely an engine mechanical problem, you think? So therefore, as you continue to read and follow the directions, and that's why I've always said, have you ever tried to diagnose by the book? Okay, I have this code. Is there reading I need to do to understand what's going on here? And in this case, it tells you to look at the crankshaft position active counter. And it says there, what you should be doing, what should be testing, and what you're looking at. So again, you're going to use your crankshaft. You're going to look at your reset counter. You should have 0 counts, right? That's what you're looking for. An engine should not stumble or stall. So therefore, you can do a wiggle test on the actual connector. And if the sensor's buried down there, I have been known to use my long pry bar or skinny screwdriver, where I can actually poke at that connector, wiggle it a little bit, and while somebody's cranking it or while running, to see if it's causing a no intermittent stalling or actually no crank. On the Duramax, on the early models, one thing I've always criticized was the fact that you got those 2 big fat connectors, and those 2 big fat connectors on the driver's side on the top, those lead to the cam and crank sensor. And we actually have wiggled at where the engine would stall, and turns out that we had a bad pins. And if you remember from the old days, we had pin problems on those connectors. But as we go to the newer trucks, it still applies where we can have actually connector issues too as well. Not as often as we used to, but it does happen. So again, following the procedures, you might get a little smarter in understanding what's available for you from the manufacturer. Very important. And as we look at other codes, such as the PL340, the PL341, which is relating to the camshaft position sensor circuit, and then again, performance, same thing, but it's the camshaft position sensor. So we have to look again at the actual, how does it work? And you'll notice it also explains, which I'm not going to read, the Hall effect sensor along with the ECM and the reluctor wheel. So another thing that some of you might not be very good at, and something we need to get up to speed, and I've been meaning, it's probably January's subject, is wiring diagrams. Okay. This is a General Motors wiring diagram. Some of you might be using the Mitchell Pro Demand diagrams. That's fine. I'm a big OE user. I like to use the OE service information. Even though I was working on the Land Rover last week and had to look at those wiring diagrams, it was better for me to use the Mitchell Pro-Demand diagrams, but I get it. But in this case, understanding how these sensors work and how they're wired is another issue. So as we look at the crankshaft position sensor here, I'm going to zoom it up. A lot of information is given to you here. Those of you that are spoiled by Ford, I'll show you a Ford diagram. Ford gives us a lot of easier information to get to, but you're going to notice there that we have our 5-volt reference coming in there. Hopefully you can see my cursor. And in this case, we got our 5 volts. So kind of questions the ground. The signal return is actually cavity 84 of the connector. And then you got your signal, which is cavity 85. Again, that is your crank sensor signal coming in. So it's the green wire, circuit number 6271, while the reference voltage is circuit 6270, which is a violet with a blue stripe. And then we got black with violet being our ground, right? But on the sensor itself, we do have the 3 different pins identifying again which is which. So again, we want to check our 5-volt reference, again, our signal return, which is our ground, and obviously our signal. Again, I reiterate, I actually had to teach this several times last week. Signal return is your ground for the sensor itself. Okay, signal return is the ground for sensor itself, and we just read it. And we also have a signal. So do not confuse the signal return with the signal. Okay. Signal return again is what? Ground. Your signal is the actual trigger or that on and off signal that you just saw on the lab scope that I just had here on my simulator. Very important to understand. Okay. Now, changing gears here again, I'm going to go back to my scope here. Hopefully it's still working. You didn't go to sleep, did you, scope? Going back to my scope, once again, if you don't see it, let me know. I'm actually going to get out of here. Now, I do have remote access of these. My laptop, even though I have it next to me, it's actually remote desktop that I'm using from Google. And what it is that it actually has the ability to control remotely. So I've controlled a few scan tools in the last few months, helping guys out with diagnosis. So that's what I'm using. Anyways, when I go to guided component test, I have a 2016 RAM 3500 logged in already. And for those of you that haven't taken advantage, I just saw some great scan tools and new tools that were out there at Apex and SEMA. And in this case, what the tool now allows me, and some of you may have seen this already, is if I'm diagnosing a crankshaft position sensor on this RAM application, there's the connector, and there I can see the ID of that connector, just like what we saw in the wiring diagram. 5-volt supply is the brown and orange wire. In this application, your sensor ground is dark blue and gray, which is also known as your signal return, right? And then you got your sensor signal, which is brown and light blue, right? But if you're going to do continuity tests between the computer connector and the actual sensor, because maybe you have a continuity issue, maybe you got no signal or no 5 volts being supplied to the sensor, obviously you want to go from the ECM straight to the connector going to the crank sensor. That helps a lot, okay? But you can also set up your lab scope. So in this case, I can look at a signal coming out of here. It tells me how to tap into it. And at that point, I can check the signal integrity with the scope like you just saw there. And when we talk about the camshaft sensors, same thing. There's my CKP, and I should have, I didn't do my homework, but it should be here. There's my cam sensor. And there's your connector, similar to that of the crank sensor. Again, explain to me what the voltages should be. And in this case, again, I can check that signal as well. Now, please note, like you just saw an on-off signal of 0 to 5 volts, you can't use your meter, in other words, digital voltmeter, because it's going to read the average voltage, which ideally is going to read around 2.5. But in this case, the true way to test the signal integrity is to actually scope it like I just showed you, which just means you connect your 2 leads from your scope, you ground the scope to a known good ground. I like to go straight to the battery. And then I got my 1 lead, and that 1 lead, I'm going to go ahead and probe to that signal itself, whether being back probing on the ECM or on the connector going to the crank. So yeah, we are back probing. So have a good back probing kit does help to actually make sure you get right to the back of those to help you out. So again, there is a lot of testing you can do. So therefore, I could log in with this scan tool and the scope, and I can actually be ready to test signals. Here's a thought. If I work on a Powerstroke 6.7, I locate, for example, the connectors and the pins, and I see that the ECM is right there on the passenger side and engine compartment, right on the bulkhead firewall, right? And I identify all the signals. What are we talking about? Probably to get the service information, to get your scope set up, to go ahead and start probing. You're talking about what, 10, 15 minutes? So if you take time to record and look at a known good signals, you'd be surprised how well of a diagnostic clinician you can be by looking at the signals of these crank and cam sensors in the event that you suspect there's a problem. So therefore it's a pretty good thing. So again, you're trying to see, do you have a signal that's actually going bad? Now, one thing I've always criticized, let me be fair here. One thing I've always criticized about doing scope testing is, let's say I got a truck that has a fishbite effect where it just kicks out. And you could see the delay or the dropout of the signal when that occurs. So again, the engine's running and all of a sudden, boom, it just wants to almost die. It's a straight, like it's cutting off. The question begs, is the sensor responding to the condition or is the sensor causing the condition? They say that's one thing that a lot of us have struggled with. So obviously we have to check other things too as well that can cause the issue. But all I'm saying is be aware that, are you looking at what's causing the condition again, or are you viewing what actually is developing because of the condition? Like, for example, the one that tops off the top of my mind is an ICP sensor issue on a 6.0. I don't know why that comes into my head, but in this case, what happens is that ICP will cause an intermittent, all of a sudden, like it wants to fish bite at you. In other words, just all of a sudden jolt. But as you look at that crank, you're going to see that signal drop out momentarily. So we know it's not the crank sensor, we know it's the ICP. So again, be aware of that. Okay. All right, let me switch back to my PowerPoint. Hopefully that's helping. But in this case, again, getting to know the wiring diagrams is very important. And down here, we can see our camshaft position sensor. Let me highlight there too as well. And in this case, we're looking at the actual camshaft position sensor there. There's the wiring, same wiring too as well, your 5-volt, your ground, and your signal itself. So again, your signal return and your ground at cavity 38. So the wiring diagram helps me a lot as long as you understand how to read the wiring diagram itself. And we'll show you other diagrams that are much more simpler. You are looking at an L5P Duramax there. But as we switch to Ford, how does Ford lay out their service information, right? Well, again, I'm a big advocate of doing it by the book. What's the book telling me to do? Maybe I'll skip some steps because I know what's going on there. But, if you're novice to this, you're going to notice that when you got a camshaft position sensor problem, there are other codes or tests that can fail, like the P0016, P034 to P0341, that can actually contribute to the cam sensor input issue, thus causing the code to set, right? So the question begs, was it a circuit issue or was it a circuit performance issue code that you got set, right? But regardless, though, it says, are there any present, are any DTs present than these codes, right? So in this case, they're asking you for that. If not, you're going to go to those codes. But then even the first step is telling you to check the voltage to the cam sensor. And obviously you want to see a voltage. Ford allows kind of a leeway, to be honest with you, which is 4.5 to 5.5 volts, which most of the time I see 4.99. That's usually the case. But again, if you're new to this, again, you want to make it a habit to diagnose following the proper steps. And as I move on with the steps, on V3, it tells you right there to check the CMP sensor circuits for an open in the harness. Right, like I told you, there's your ECM and there's your sensor, and there's wiring in between, and there may be connectors in between that could be causing the issue. Again, it's telling you which pins to go to, and at that point, you can test for continuity. So a lot of us that are not very good with electrical are savvy at this, but it's just a matter of you taking the connector off. I mean, I do it at shops. I just did it quite a few times these last 2 weeks at shops. And it's just a matter of you just going ahead and back probing, know how to back probe, because we did have a few back probe issues with some of these techs, but overall they got it and they could get a signal. Again, the 5-volt reference, the reference ground, and also the signal itself, right? So, and then you got resistance tests that you're doing on that harness that they're saying no more than 5 ohms, which I think is quite a lot. But as I continue looking at the PID list from Ford on the 6.7 liter, you're going to see, and let me use my pin here, you're going to see that that there is a CMP fault PID, right? So in the event that there is a fault issue, on your scan tool, it's going to address that there is a fault that you can actually read there, which will help you again identify, do I have a cam or do I have a crank sensor issue? In this case, you can see a cam input. Now, it doesn't provide one for crank. It just provides one for the cam sensor that you can read off of your PID list from your scan data. So it's just a matter of looking at this to understand that. So, and then as we look at the wiring diagram, Ford makes their diagrams a little nicer. If you're an Identifix user or you're using Motorcraft Service, or maybe you have a subscription from Ford, well, obviously the wiring diagrams are beautiful on Ford. They're my favorite. I'm not going to lie to you. Those of you who don't know, I could just click on a connector, which is a hyperlink, and that'll go ahead and show me the connector in view. And also I can click on the C12232 right here, and it'll actually tell me which pin is on the ECM connector. So it's a sin if you don't scope a signal, for the simple reason that it's right there. The ECM is right there on the passenger side on these 6.7s. Yeah, the 6.7 Cummins stink because those computers are buried on the side of the computer. You literally have to get in there, probably take an inner fender off on the driver's side or the wheel off just to get to those C1 and C2 connector there. So they're no fun to get to. But again, the signals haven't varied, but you're going to notice though, there's your signal return right here. And we've been saying that signal returns your ground. So obviously the CKP must be your signal. So the other wire must be what? This one coming in here is, this one must be what? This one's got to be the what? Your actual reference voltage that's shared with other sensors. So therefore that's got to be your reference voltage. So, and you're going to notice that the grounds are all shared together among the EGR valve. And again, the exhaust pressure sensor and the map sensor itself, they're all using the same ground or signal return. That goes back to the PCM, as you can see that I circled right there. However, though, again, the signal wire is this yellow orange wire that's coming off of pin 3 of the connector from the crank sensor itself. But again, this must be, again, our reference voltage, which is being shared with other sensors too as well. So not with these 3 that are shown, but it does share the same ground, which kind of tells you that if we have a short to ground or an open somewhere on that 5-volt reference, it will affect the crankshaft's ability to generate any kind of signal. I guess what I'm trying to say is that it would be a sin that you replace a crank signal without verifying the 5-volt reference. But again, a lot of you will ground the meter and go ahead and measure the 5-volt reference. That's fine, but you need to verify that ground, right? That signal return. So therefore, I like to go between pin number 1 and pin number 2 on the connector itself of the crank sensor right there. And in this case, it'll help you again diagnose that you ensure that you have a ground and 5-volt reference going to the sensor itself. So don't screw up there. So therefore, want to do that. But again, as I go back to G, you're going to notice G comes back right here, and you're going to notice that yes, I went back 1, and you're going to notice right here, this is the wire that actually goes back to your 5-volt reference. Now remember, those of you not that may or may not know, 5-volt reference is also has a diagnostic trouble code it can set. So therefore, you may have a re-ref code if there is an issue with that 5-volt reference. So there you go. And then when you look at the camshaft position sensor on these 6.7, same thing. Again, you can see the VREF is dedicated. So therefore it has its own dedicated 5-volt reference. Go in there to terminal 1. And obviously our signal wire is terminal 2. And our signal return is ground, as you can see clearly here on the ECM and on the diagram. So they gave us a good help in giving us that information right there with the cam and crank sensor on this application. So I know it sounds basic to some of you, but some of you are not testing these. Again, you're just putting a sensor and you're not checking the circuits. And those of you that always struggle with location on where different sensors are at, Ford does and other manufacturers give you good diagrams showing you where everything is at. And in this case, there you can see the camshaft position sensor located in the front. Again, you can see that connector 180, and you can see the sensor right there. While the crank is in the back, but again, it's not in the front, it's in the back, facing towards the flywheel, if you will. So in this case, some of you know about the horror stories with that sensor too, and how that reluctor wheel need to be careful with it when you're actually putting that flywheel back on, right? So, but as I switch gears and look at a Cummins, here's this a Cummins diagrams from Ram or Dodge, as you want to call it. Same thing again, nothing is different. Again, cam sensor ground, but they call it a cam sensor ground, and you can see a crank sensor ground. So their terminology is a little bit different. There's your 5-volt supply, and then you got the CMP and CKP signal wires. All color coded, telling you which pin is which on both the sensors and on the connectors, which in this case, they're both on connector 1 of the ECM. All your Cummins applications, as long as I can remember, have a connector 1 and a connector 2 on the ECM. Again, it's telling you which cavity it is. There are 2 big connectors going to that ECM on the side of the engine that you see there. So with that said, as we look at their information, I'm not going to read this all, but again, there is the theory of operation they like to call it. It is also Hall effect. It's also using a 5-volt reference. So again, it's telling you how it generates the signal. So again, one of the things I tell you about learning your sensors properly, right? But what I like about RAM is the fact in the service manual, in that code for this, whether it being a 335, 336, whatever it might be, it's telling you possible causes. So in this case, damage to the crankshaft position sensor. And if you lose a belt on any 5967, it could hurt the actual sensor, especially on the 59s. So it could also tell you there's damage to the wheel itself. They call it a tone wheel, the Reluctor wheel, same thing. Mechanical misalignment of the CKP or CMP, that can happen, and mechanical misalignment of the crankshaft and camshaft gears, whether being a tooth off or there was some serious engine damage or something shifted dramatically. But as I look at RAM service information, when I'm in genuine RAM service information, either through Tech Authority or through Identifix, one thing I like to see is, what is going on or what are the sensors we're going to see set. Now, obviously, you got your misfire code family right there, which is the 301 to 306 codes. And then there's your 335, which is your circuit and your sensor performance. So again, these codes seem to be generic. And as we know, they're generic because they're PO codes. PO codes is generic, mean the same thing across the board, which we just saw earlier with General Motors and Ford. But in this case, we can see now with the RAM, same thing. But then right afterwards, we got our cam sensors. So those of you that like to cheat a little bit, when I'm looking for wiring diagrams, I often cheat with RAM and just look at the DTC diagnostic chart here, and I'll just look for the appropriate sensor. So if I want circuit code, I'll definitely, for the cam sensor, go to PL340, right? And if I want to look at a circuit code for the crankshaft position sensor, and I want information on it, I'll go to PL335, so therefore that does help. So again, when I look at the crankshaft position sensor, along with we just saw cam, again, same thing, 5-volt supply and so on. So it's relatively all the same across the board from the big three, whether it being Duramax, GM, whether it being Ford 6.7s, or whether it being Cummins on the 6.7 side. But again, these issues can cause various different codes. And again, you're going to see all the different issues. 5-volt is shorted to voltage. The 5-volt circuit shorted to ground, somewhere in that wiring harness. And by the way, we have seen this shorted to voltage internal in the sensor. So be aware that we can have a real defective sensor, especially in the aftermarket, but I won't name names. But anyways, we see our, shorted to crank sensor circuit, ground circuit. I mean, the list goes on and on, all the different aspects of what can occur. So another reason for you to keep in mind, don't underestimate the power of the wiring and the issues it can give you, so therefore you want to look out for. And that's why, again, I told you earlier that technician abuse is something I see a lot when it comes to the wiring connectors and harnesses. We got to be easy on them. And sometimes we got to replace pigtail connectors. And those pigtail connectors, the plastic lock is broken, something is broken. So with that said, can't say enough. Last but not least, who could be the most horrifying issue? It could be a PCM, right? Internally, that whether being pulled down or pull up resistor on that PCM can also be an issue as well. So again, you outline the way RAM shows their service information. I try to keep it as how the way they show it. But again, if you're looking for some structure, instead of just, imagine this must be that, how do I do this? Note that they have their service procedure. And again, voltages and resistances that you want to stay under. Same thing for these 3-wire connectors going to the sensor. So there it is. All I'm just trying to show you again is understanding what you have available there for the sensors themselves. So that's why I've always said, you always got to know your sensors. And here is a good example of knowing your crankshaft and camshaft position sensors and what signals they should generate for you to diagnose it. Like I said before, you're checking for the integrity of that signal. So speaking of signals, those signals could be analog or digital that we frequently see, but for the most part, crank sensors and cam sensors are going to be digital on off like we saw earlier, but they can also be AC in nature. And like I told you already, like it says on the bottom of this slide, AC voltage signals are buffered by the ECM and PCM. For example, on a 6-liter, you're going to notice that they're using variable reluctance sensors. So the CKP is generating an AC signal along with the cam. And what it does is that it syncs itself with the with the cam sensor, and eventually you get that FICM sync. So for the longest time, we can look at a sync signal, and we can look at the FICM sync to see if it's yes or no. So in this case, we see clearly that it's translated from AC to DC because the signal shared between the ECM and the FICM, fuel injection control module, is a on-off square wave DC signal. So if I were to be able to scope one, I would see an AC waveform, and then we would see our DC square wave signal. So again, who did the translating or the converting, like it says at the bottom? It's actually done by the ECM, PCM, depending what you got, depending on the setup. So therefore, what Ford provides on their service manual, and if you've been to the coffee table books that Ford provides, they have little sections talking about the cam and other related sensors. And you can see here, they're showing you that it is using a SIG signal, and your average voltage is 0.5 of a volt. But in this case, as the motor changes RPM, the actual amplitude or the height of those AC waveforms from peak to peak actually changes. Regardless, though, we can look at those signals. So in the past, like I said, as you can see on the upper left, as I play this recording, you're going to see that these, again, they actually create a sync signal and a FICM sync. So it was easy as checking to see if I had a what? Do I have a yes signal or do I not have a yes signal? Okay, that's again the FICM sync and the sync that you should be able to see up there on the upper left there. So as the engine starts, let me mute the sound. You'll see a crank event there. So therefore, again, we went to yes. Yes, I stole this from my 06-liter class. I still had the recording, but again, you can see the yes signal there upon crank up. So those of you who didn't see it, let me play it once again. Those of you new to this, that's why you need to set up your data. Again, you can see these change to yes. So that tells me that the cam and crank were responding correctly, right? So if there was a no, then it's a cam or a crank issue there. So Ford, again, in their coffee table book, since we're talking about Ford right now, have always given us, again, a good charts and good information about sensors themselves. So there you can see the crank signal generating an AC, and then you can see the crank output. And the reason why they call the CKP out is because it is a DC signal, while the AC in is the AC, I guess the signal in is actually going AC in nature. Again, the PCM, ECM changes it to a crank output. And again, they're showing you the reluctor wheels along with the teeth themselves, showing you how it actually sets the trigger, right? Like I told you earlier, on these engines and the 6.4s too as well, can the thrust play really lose a signal? Yes. And some of us, if you look at different forums out there, you're going to see where they had to shave the sensor to get a better signal. So then at that point it syncs. But that to me was actually a what? Is actually a, I guess what I'm saying, a defective sensor issue that we have seen. So therefore, again, to review, got to test those circuits. Again, the reference voltage, your signal return to ground, your signal wires, and signal waveform. Again, the waveforms themselves must be inspected. Here we saw DC earlier live with my simulator. Here you can see a actual, Powerstroke 6-liter here with the AC signal actually being generated. Again, one's your cam, which is the bottom, and then you got your crank on the bottom, on the top, excuse me. So top crank, lower cam, and you could see the AC signal. So again, that's something we can see there. So obviously, as the engine RPM is increased, which I didn't do on this one, we should see the amplitude. In other words, it should get taller because it generates more voltage as it spins more faster on these variable reluctance sensors. So in time, if you want to know if these sensors are working properly, it's a great thing to actually know what their peak to peak voltage is. Obviously we can look at RMS voltage, but we need to look at the peak to peak. That's primarily what I'm looking at, and how clean the signals are. And you'll notice these are pretty damn clean signals that you're looking at here. This is how clean as they get. Some scopes will show much more smoother, but this one that I'm using here is doing a pretty damn good job. So therefore, again, the sky's the limit on what you scope. You just need to take advantage of, again, scoping first on a known good truck. And come on, a lot of you I know have many Duramaxes, many Cummins in your shop. Why not take some time to actually, let's look at these signals, how they look. So when I do have a drivability problem, whether being no RPM signal, in other words, crank no start, or a drivability, I can know what I'm looking for. So pretty good. I hope it does help. But that in turn will affect your monitors. It will affect your misfire diagnosis and so on. So therefore, we got to keep that in mind when we do our diagnosis. Okay. Can't say enough about that. So therefore, definitely want to pay attention to that. So, but like I said already, I decided to shoot this image there. Again, the reluctor wheel integrity has a lot to be desired. Like you can see here on this early LB7 LLY application, you can see the crank gear on the bottom. There you can see the reluctor wheel in front of the crank gear. And in this case, those reluctor wheels were known to come loose. That it still happens from time to time. So in this case, you'll notice the locations that are often shown of where these sensors are located at. But again, I make it a habit when I want to inspect, especially these front reluctor wheel, not like this. The Powerstroke 67 is different, but I like to look at the teeth, the reluctor wheel. So therefore, don't be afraid to take that sensor out and stick a borescope in there. Obviously, don't touch the reluctor wheel. You don't want to break your scope, but in this case, put it in enough so you can have somebody crank it and you could see how those teeth look to see if they've been externally damaged. Definitely want to pay attention to that. So very important to do. Hopefully that helps you there. So, well, that pretty much as I guess I forgot to put the other slide in there, but how did we do? Big topic, easy subject in my opinion, but it's a big topic in terms of crank and cam. Hopefully, yeah, if you want to give me a email at tsalas@dieseltg, and I'll put it on the chat there. So those who don't have my info, but definitely want to make it a habit of reading the codes circuit, or like I said, do you have a performance issue? And two is understanding the wiring and how you can do proper testing. So what do you think, Mr. David?
I think that was great. A lot of very, very good information. I was thinking actually while you were talking there, we really appreciate all the real world examples that you give us, as well as the graphics and the diagrams, the wiring diagrams, and the actual scope, samples there and so forth. It's really good material. So as somebody put in here, it's not cheap education, it's valuable and priceless. And that's really, really true. So we very much appreciate all that good information that you share with us every single month. I just wanted to remind everyone that this will be posted on the Lucas Diesel Systems YouTube channel. Tony will post it on his website. You'll be receiving a certificate as well. And for those of you who are in the diesel fuel injection side of the business, think Lucas for your fuel injection needs. And for those of you who will be attending HDAW here mid-January, only about maybe 3-4 weeks away, we look forward to seeing you there. We'll have our usual booth at HDAW. Come by and see us, and come see what's new at Lucas, because we've got a lot of new things coming along. The next webinar is tentatively, and it's not set in stone, but it's actually tentatively January 28th of 2025, which is creeping up pretty quickly with us. So with that, I don't see any other new questions for us, Tony. Other than very much thank yous.
And wish everybody a happy holiday, Merry Christmas, Happy New Year.
Yeah, I echo that. Very much appreciate that.
May Santa bring you all the gifts you want.
Yes, exactly. Exactly. A new scope and so forth.
There you
Things
go.
like that, right? Some new tools. So with that, I'd like to thank everyone for participating. Thanks for taking that hour and something out of your day. We very much appreciate that. And we look forward to seeing you again towards the end of January. So happy holidays and see you soon. Thank you very much, everyone. Goodbye.
Bless everybody.